Hello everyone, I welcome you all to the fourth lecture of week 3. The week 3 we are looking at various selection and fabrication criteria and methods which are required to build an automated system. Well, in this lecture we will be learning at primary level various fabrication processes. The outline of this course is as follows. At the start of the lecture, we will have an overview of various fabrication processes which are used. Then we will see the basic manufacturing processes such as casting, forming, joining and machining. In addition to that, the next generation manufacturing process, that is the additive manufacturing process, we will see at a introductory level. So, well my friends, what we have seen in the previous lecture. So, let us have a quick review of the content that we have seen in the week 3 lectures. If you remember, we have seen the selection criteria for electrical and electronics components that are required to build an automated system. After that, we studied various technology terms related to electromechanical systems. Electromechanical systems in general and sensors in particular. Then we have seen various CAD based technologies required for design and fabrication of the automated system. Now comes how to manufacture various elements of an automated system. Let us look at what are the various components which are there in a typical automated system. A typical automated system may have electrical components, electronics elements, the structure or the body of the system. The structure or the body will have the skin or the housing, or you can say the cover, and the automated system will have a variety of mechanisms. So, these are the mechanical elements. Of course, the structure, cover, housing and skin are also the mechanical elements. The electrical components and electronics elements we have to select based on our requirement and then procure them. So, standard parts which are available such as the electrical drives, various sensors, actuators, signal conditioning devices, microprocessors, all memory elements, all these elements the designer has to choose and the company has to purchase from the market. In previous class we have seen the criteria in detail. In today's class we will be studying how to manufacture the mechanical elements. So, in this mechanical elements, some of the elements again are possible to have in a ready-made format, no need to manufacture them in house. But some of the elements are to be designed and manufactured in house. These are the customized elements, these are the customized parts required to build our manufacturing system, our automated manufacturing system. Now, let us see what are the various elements that you can easily procure from the market. If you look at the construction of an automated system or any machinery or a machine tool, you will find that there are various components, such as the automated system will have various components such as screws, bolts, studs, nuts, washers, rivets, wires and ropes. So, all these elements are used as temporary fastening elements. So, if you want to assemble the sub-assemblies or various parts of our system, we need to fasten them together. So, we can have either a temporary fastening or the permanent fastening. So, to have the temporary fastening or semi-permanent joining, we are using the screws, bolts, nuts, washers, rivets, wires and ropes. In addition to this, we require pins, clips and toggle clamps. So, pins are required again for the fastening or the location purpose, for fixing purpose, and the clamps are required to hold the parts, to fix the parts. We may also require various springs plungers or indexing plungers. The system also require hinges, locks, latches, various levers to operate the machine tool or to operate the automated system. For the operation of the hydraulic system, we need to have the plugs. The system also required to have caps and seals to avoid the leakage of the liquid. There are various slides, handles, hand wheels. They are incorporated for handling of various parts of the system. Various knobs are also there and wheels for maneuvering of the system, for the conveyance of the system from one location to other location. The automated systems are working on application of variety of forces. So, in the application of the forces, there may be chances to have the vibrations in the system. So, we also require to have various dampers. So, my friends, all these components are readily available in the market, only we have to choose a proper element, we have to finalize the specifications as per our need, and then we have to go for purchase of these components. However, as I mentioned in my previous slide, what are the various things that need to be designed and manufactured in-house? In particular, if you look at the construction of a typical automated system, we may require to have a bed or a base or columns. So, bed, base and columns are made up of metals. On these basic structural elements, we are putting up various sub-assemblies, and these sub-assemblies may be spindle head, speed box housings, various tables, various carriages, so on and so forth. So, all these sub-assemblies will be integrated on the bed or base or the columns of a typical automated system. Well, these mechanical elements, as I mentioned, are particularly manufactured by using metals. In metals, mainly the cast iron and steel are used to fabricate these elements. So, cast iron provides higher damping characteristics. The cast iron has very good toughness. So, in case of application of the dynamic loading, in case of application of the intermittent loading. The cast iron will absorb the vibrations very easily. The cast iron also provides better sliding properties. The friction would be less and the wear and tear of the cast iron would be less. The steel material also has good damping properties, but the strength of steel is higher during the static and dynamic loading. The steel has, well, there are certain other metals such as copper and aluminum are also used in the construction of an automated system. In addition to this, there are certain non-metals such as polymers, polycarbonate sheets and glass. These are mainly used to prepare the housing or the cover of the automated system. Now, as far as the manufacturing or the fabrication of the automated systems are considered, let us consider the part 1, part 2, part 3 and part 4 are nothing but the bed, base or the columns, the spindle head, the table carriages or the skin of the automated system. Now, as I mentioned, we need to design them and fabricate in house. So, for that purpose we require the raw materials. So, from where we are getting the raw materials? So, we are getting the raw materials from the mother earth, from the nature, and the conversion of the resources available from the mother earth into raw material. So, this is basically being done by the mining and metallurgy branch of engineering. So, we need to convert the raw materials into the final product that is required for our intended purpose for the fabrication of the automated system. So, to convert the raw material into finished or semi-finished product, we need to carry out certain operations, and these operations are grouped together as primary forming operations and the casting operation. The primary forming operations converts the raw materials into basic shapes such as rods, sheets and bars. The raw material which is available in the form of, if it is fine with you to work with the available shapes of the raw materials and use them for making the final product through the other set of manufacturing processes, say the joining, finishing or assembly, it is okay. However, in certain cases we need to change the shape of the primary formed components. So, for that purpose there is another set of operations need to carry out, and these are called as the secondary forming operations. In primary forming we are getting rolled sheets, extruded bars and rods. If it is fine with you to use the sheets as it is for making the final product, for making the housing, it is fine. But we need to carry out certain operations on the sheets. For example, we need to have some holes, some notches on the sheet. So, for that purpose we have to carry out another operation on that, and that punching operation, the notching operation is nothing but the secondary forming operation. If we are having bars, so we are using the bars directly for the welding operation. We want the bent bars for our construction purpose. Bending operation is the secondary forming operation. Some parts need to be manufactured of the required size and shape by using the casting operation, but the casting operation will not be providing us a good quality surface finish. The surface may have the dust, dirt, the surface may not be as per the required accuracy. So, for that purpose we need to carry out a finishing operation that we call the machining operation. The machined castings can be utilized to make the final product. So, friends, we will see these manufacturing processes one by one at a preliminary level. The first process is the casting process. Casting is the oldest manufacturing process, and it is considered as first step in the manufacturing. It is a first step in the manufacturing. We have to carry out the casting operation. So, the principle of operation is very simple. We are making a mold cavity. So, this is a mold cavity. This is the sand mold, very typical and basic casting process. The green sand casting. This is the gate. Gate is the opening through which we are pouring the hot metal or the molten metal. This is the riser. Risers are used to allow the proper settling of the molten metal inside the mold cavity. Now, we are using the saddles to carry the molten metal. So, we have to first heat the metal. Metal is to be heated. It will be converted into its liquid state. The liquefied metal will be poured into the cavity. Then that poured molten metal will allow to solidify, solidification, and that solidified product will further be cleaned. Then we are trimming off the gate and risers, trimming, and then we are carrying out the machining operation. So, ultimately after removing of the product from the mold cavity, so either the mold can be reused if it is possible, or in case of the green sand mold, the mold is expendable. So, it is of only one time use. So, we have to discard it, we have to recreate another mold for the second attempt. Well, in casting process we can achieve whatever the size and shape that we want of the final product. However, we are changing the thermal properties, we are changing the material properties of the material. So, whatever the thermal properties of the constituting elements of the casting will be changed, will be modified after this liquefaction and solidification process. The designer or the process engineer should know about the melting temperatures of the job and mold material, then solubility and chemical reaction between the job and the mold materials. In addition to this, it is essential to know the thermal properties, mainly the conductivity and the coefficient of thermal expansion of the material of which we want to prepare the casting. So, the conductivity and coefficient of thermal expansion. The coefficient of thermal expansion will decide the machining allowance. There are various types of casting processes that are used in the industry, and these types are dry sand mold, shell mold casting, investment casting, gravity die casting, and die casting. And there are many other manufacturing processes as well of the casting. The dry sand mold casting is a very typical casting process, and it is used to manufacture medium to large size of casted products. Shell mold casting is used to manufacture medium size components. The investment casting process used to manufacture small size parts at a mass scale. The gravity die casting and the die castings are used again to manufacture the metal components of medium size. In sand mold casting, we are using expendable mold, which we are using only once. So, when the sand is mixed with clay and water with certain organic additives, so we get the green sand mold. So, in general the sand is in the proportion of around 70 to 85%. The clay is about 10 to 20% of the total volume of the mixture. Water is about 3 to 6%, and the organic additives are in between 1 to 6%. So, what are the various organic additives which are used? These are wood flour, dextrine and sea coal. So, this wood flour, dextrine and sea coal are used to improve the properties of the mold cavity and to give sufficient strength to them. When we bake the green sand mold at temperature about 100 to 250 degrees Celsius for several hours, then we are getting the dry sand mold. The dry sand mold has sufficient strength. It can withstand the fluid pressure during the pouring operation and the temperature of the molten metal inside the mold cavity. Now, let us see where these casted components are used in the automated system. On your screen you can see the interior of a CNC machine tool. So, there are various structural elements that we can locate. This is the bed of the system, this is the column. There are more elements which are mounted on the bed over which the table will be mounted. So, all these elements cannot be outsourced. So, we have to design them and we have to fabricate them in house. Well, the next manufacturing process is forming process. In forming process, we are applying mechanical stresses on the work part or the raw material, and then we are getting the desired shape and size of the product. So, when we apply the mechanical stresses, there is a plastic deformation of the work part. So, what kind of stresses we can apply? We can apply tensile stress or compressive stress or shear stress or combination of these stresses, but the stresses should be more than the yield strength of the material, and these stresses should be less than the fracture strength of the material. So, these stresses will be generated by applying the forces. So, you can apply tension or compressive forces, or you can apply forces which are generating the bending stresses, shearing, or a combination of these. The peculiarity of forming process is that we are not losing any material. So, whatever the raw material is there, that would be reshaped by using the application of the forces. That is why the process is inexpensive. There is no wastage in this process. Whatever the energy that we are inputting, whatever the energy that we are applying during this process will be help to improve the material properties. The strength of the material is getting improved during the application of the forces, during the application of the plastic deformation, and that is called as the strain hardening. There are basically two categories of the forming process, and these are based upon the application of the temperature, application of the heat energy during the process. The first group or category is cold forming process. So, this forming process is occurred at room temperature. There is formation of strain hardening. the strength is getting improved, the improved hardness sometimes lead to increase in the brittleness of the material, and such brittle material may not be useful for certain application where the ductility is envisaged, where the ductility is desired. The next group is hot forming process. Here we are applying the heat energy, and when the temperatures are above the recrystallization temperature, then we are applying the mechanical forces. During this hot forming process, we are getting large plastic deformation and the strain hardening would be less. Now, let us see what are the various forming processes which are used in the industry. These are rolling, forging process, drawing process, bending, extrusion, punching and blanking. All these are some of the basic forming processes. In addition to that, there are many. Now, let us look at the first process, that is the rolling process. In the rolling process, we are having a set of rolls, roll 1 and roll 2. These two rolls are power driven rolls, and we are maintaining a constant gap between these two rolls. These two rolls are rotating simultaneously, but their direction of rotation is opposite. So, when we feed raw material in the form of a sheet, so this is the raw material. The raw material comes in the gap between the roll 1 and roll 2, and it will be driven, the raw material will be driven due to the friction at the regulated opening between two power driven rolls. So, the rolls are getting the material inside and they apply the compressive forces. That compressive forces are generating the friction, and then friction will lead to plastic deformation, that is the reduction in the thickness of the material, that is the raw material. So, at last we are getting the finished product with reduced thickness. Now, this rolling process is not only used to reduce the thickness, it can be used to manufacture various shapes as well, such as we can have the rail shape or various channels, angles and even the round bars. So, to achieve these various shapes, we have to give the required contours to the roll. So, instead of using flat rolls, we can have the contoured roll. So, certain applications are there on your screen. So, these are roll sheets. Then you can see the eye channels, which are often used in construction. In addition to that, we can produce variety of angles and the C channels. So, here you can see the inverted T shape channel. So, all these channels can be manufactured by using the rolling process. So, this is the L channel. So, in addition to this basic rolling process, there are the other process, as I mentioned, the forging process, the drawing process, extrusion process. In all these processes, we are applying the mechanical energy and we are plastically deforming it. The forging process is hot forming process. We are increasing the temperature of the material, we are heating it up, and the temperature should go above the recrystallization temperature, but it should be less than the melting point temperature, and then we are applying the mechanical loads over the material to get the required size and shape. So, forging can be open die forging, or we can use the dies to get the required size and shape, that is called as the closed die forging. The next manufacturing operation is the machining operation. Casting and forming are the basic manufacturing processes. However, there is a movement of particles during this operation. The casting has inherent problems of high accuracy. So, we cannot achieve the accurate work part as desired. This is basically due to the shrinkages that is going to occur during casting resolidification process. The resolidification is very complex phenomena. It is very difficult to control. That is why it's quite challenging to get the required accuracy during the casting process. Well, we are heating up the material and then cooling the material. So, naturally there is change in material properties, modification in the material properties. It may not be desired in certain applications. The second operation, that is forming. The forming is having inherent problem to handle large size components. Very heavy components are difficult to handle during the forming operations. Then it is very difficult to generate complex parts if you want to manufacture thin walled parts or the parts which are having complex geometries. These are difficult to manufacture during the forming process. Some of these limitations of casting and forming process can be eliminated by using the machining operation. In the machining operation, we are getting the desired size, shape and surface finish by removing the excess material from the original material. So, this is the most versatile manufacturing operation. In our previous lectures, we have seen the milling process. In the milling process, we are using a rigid body, that is tool. The strength of the tool is much higher than the workpiece. There is a relative motion between the tool and the workpiece, and the mechanism or machinery which is providing the relative motion between the tool and the workpiece is called as the machine tool. So, there is a primary cutting motion, the tool is rotating at constant speed and we are feeding the uncut portion of the workpiece to the tool. As the tool comes into contact with the workpiece, there is a plastic shear deformation, and in this way we are removing the material in the form of chips. The relative motion of the workpiece and the tool in predefined path will generate the required shapes using the milling operation. One of a very complicated shape can be seen on your screen. This is the capability of the multi-axis CNC milling machine. Here you can see a turbine blades. These are manufactured by using multi-axis CNC milling machine tool. So, you can see the tools and the workpiece. This is the tool and this is the workpiece. So, here the workpiece is inclined, we are moving the workpiece with respect to the tool, or we may have a configuration where the tool is moving, we are giving the multiple degrees of freedom to the tool to get the required shape. Well, in addition to the milling process, there are various processes such as the turning. We carry out the turning operation on lathe machine. Shaping operation and planing operations are used to generate plane surfaces or flat surfaces. The flat surface may be the inclined surface as well. Broaching is an interesting application. In broaching, we are generating the spline, or we can generate the keyholes in a circular parts that you can see here. The tool is having the teeth with gradual increase in their size. So, this gradual increased teeth are generating the required shape in the work part. So, here we are having the reciprocating motion of the tool. In turning, we are having rotary motion of the workpiece and translatory motion of the tool. In milling operation, we are having rotary motion of the tool and translatory or linear motion of the workpiece. In broaching operation, we are having the reciprocatory motion of the broaching tool and the workpiece is stationary. Grinding is a well known example. Here we are using the cutting tool in the form of particles. So, these particles are bonded together by using a binding material. The grinding material is utilized to remove the material in the form of very small chips and to get the required surface finish or to generate the required surface shape. When we are using the loose abrasive particles for finishing operation, then that is called as the lapping operation, and when we are using the abrasive particles in the form of sticks, that we call the honing operation. The lapping and honing are the finishing operation. In the lapping and honing, the tools are in terms of fine particles or fine powder. So, when we are using the unconventional mode of energy, unconventional type of energy which is used in material removal process, these processes are called as the advanced machining process. Many a times it is very difficult us to process the high strength material, say tool steel. So, for that purpose the contact type mechanical processes may not be sufficient to generate the required surface finish and the shape. So, in this scenario we are using electrical energy to remove the work material and to get the required size and shape or to cut the work part. There is another example of the thermal based advanced machining process is laser. Here we are using the photon energy to generate the heat energy, and that heat energy will be utilized to cut the material or to machine the material. In addition to the thermal energy, there are certain processes they are using the chemical energy. So, that process is called as electrochemical machining operation. In certain cases we are using the water to machine the work parts. That process is called as the water jet machining operations. Well, the next group of manufacturing processes that are often used in the fabrication of automated system are the joining processes. So, we have seen the casting process, forming and the machining process. These processes are generating, they are fabricating the required work parts. But in many cases it is not possible to fabricate a very complicated shape part. It is very difficult to manufacture complicated shape work parts. So, we have to generate this complicated work part by using the joining process. So, we have to divide this complex system into small parts and then we can join them together by using variety of process. So, in joining processes we can have a variety of variants, and these variants can be categorized based upon the type of bonding. So, either we can have the mechanical bonding of the work parts that to be joined, or we can have the atomic bonding. So, when the work parts are bonded together temporarily using the fasteners or the screw elements, that we call the mechanical bonding, temporary mechanical bonding. But we can have the permanent mechanical bonding as well. So, for that purpose there are many options are available to us. Rivets can be utilized, the work parts can be stitched together, we can staple them together, we can use stapler pins. We can have the shrink feet. The shrink feet, for example, if you want to fasten mechanically two tubes, the diameter of one tube is larger than the other tube. So, we can insert the smaller diameter tube inside the larger diameter tube, and then we apply the force, the external force on the overlap region of the outer tube or the larger tube with the smaller tube. So, due to application of the force, we can have the shrink fit permanent joint. In atomic bonding process, the materials are bonded at atomic level. So, that bonding can be carried out in solid state, or we can liquefy the materials that to be joined by application of energy. That process is called as the liquid state atomic bonding, or there may be a process where solid and liquid both the states are present. So, that is a solid liquid state atomic bonding processes. The liquid state bonding can further be classified into two groups. First is the application of electrical energy to liquefy the material, and the second group is application of chemical energy to liquefy the material. So, when we apply the electrical energy, we can generate arcs, that is very popular or very common welding manufacturing process, that is the arc welding process. We can carry out the induction heating in between the two work parts, and that induction heating will melt the materials and then we can fuse them together, that is the induction heating. The heating which is generated due to the resistance between the flow of electric current between the two work parts, so that is called as the resistance welding. In the other group, that is the chemical based liquid state atomic bonding process, so we are using the gases, the gas welding, oxyacetylene combination of gases are used to generate the flames, and that flames are used to get the required fusion operation. Then we can have a special welding process, that is the thermit welding process, which is used for the on-site repair of the rails. So, here also we are getting a chemical reaction, and that chemical reaction is generating the heat, and that heat will be utilized to weld the parts together. The solid liquid state welding group can further have variants such as brazing operation, soldering operation, or the adhesive bonding operation. In adhesive bonding operation, we are bonding the parts together by use of an element that we call the glue or adhesive. By applying the pressure and temperature, we can have bonding of two thin sheets. The strength of adhesive bonding is not that high as of the liquid state atomic bonding. In solid state atomic bonding process, we can join two different solid parts by using the friction process. So, we can apply the frictional force in between the two parts and then we can join them together. So, in typical fusion welding process, as I mentioned, we need to melt the work parts that to be joined and then allow them to cool down. So, melting and then cooling, which will lead to the solidification. When two molten parts we are taking very close to each other, when we are having a contact of two molten parts, so there is the fusion will occur. There is another categorization of the welding operation, and the first category is the autogeneous welding. In autogeneous welding, there is no external material that we are applying during the welding process. So, the two parent materials will be joined, and in general the solid phase welding process and the resistant welding processes are the examples of autogeneous material. But if you take example of the arc welding process, in arc welding process we are using an electrode. You might have seen a typical arc welding process at the fabrication shops. In the arc welding process, the electrode is the filler material. We are getting two work parts, there would be a gap between the two work parts. We are generating the arcs by application of the DC power source or AC power source. That arcs are generating the heat, and that heat is melting the work parts. In addition to the molten work parts that to be joined, the electrode will also get melted, and that electrode will get fused with the two different parts. The material of the electrode would be similar to the parent materials. So, when the material of the electrode is similar to parent material, that process is called as homogeneous welding process. So, arc welding, gas welding and the thermit welding are some of the examples of the homogeneous welding process. But in certain cases it is not possible to use the similar kind of electrode for the joining operation. That variant is called as the heterogeneous welding operation. So, in this process the filler material is different from the parent material. The situation may occur when we are trying to join two different materials such as iron and silver, which are not soluble in each other, they are insoluble in each other, but we need to join them. So, to join such insoluble material, we have to use a filler material. The filler material should be soluble in both the parent material. So, here we can have an option of copper and tin. The copper and tin both are soluble in iron and silver. So, we apply the heat energy, we melt the copper, and that molten copper will be utilized to join the iron and silver. So, soldering and brazing are the examples of the heterogeneous welding. So, when we used copper based alloys as filler materials to fill the gap in between the parent bodies, that process is called as the soldering operation. And if we use the lead tin alloy to carry out the heterogeneous welding operation, that process is called as the brazing operation. The temperature range of the soldering and brazing is less than the arc welding process. At lower ranges we are working during soldering and brazing operations. The next manufacturing process, which is nowadays often used in the development of automated system, is the additive manufacturing. The additive manufacturing is basically the generative manufacturing process. We are not removing anything from the parent material, we are adding the material to the parent material, and then we are building up the product. So, in this process the work parts are generated by adding the material. So, that is why it is called as the generative manufacturing process. It basically comprises the solidification and bonding of the material. So, we are liquefying the material, and then the material will be allowed to solidify. During the process of solidification, it will get bonded to the layer, it will get bonded to the other material. The additive manufacturing is very useful in the development of the prototyping. The engineers are using the 3D printing or the additive manufacturing processes to develop the prototypes, and these prototypes or models, these prototypes and models are useful for the visualization of the product shape in its early phase of development. So, if you recollect the product life cycle, so there is a function that we call the product conceptualization. So, to conceptualize the product, we have to visualize how the shape of the product will be look like during. So, to visualize that, we can use the prototyping based on the generative manufacturing process. But nowadays we can also manufacture final products using additive manufacturing operations. On your screen you can see a typical product that to be manufactured using the generative manufacturing process. In the generative manufacturing process, the required geometry would be converted into layers, and we are developing the final work part by joining these layers. So, by adding the layers one above the other. So, in this process we are generating 3D model or the geometry by adding 2D planes or 2D work parts. So, here you can see all these are the 2-dimensional. So, in generating manufacturing, a 3D model is built by slicing its geometry into the finite number of layers, and that layers are bonded together by using variety of method. The process of building up these 3D models or 3D products can be seen on your screen. To get the final product, we need to first develop its computer model, or we can call this computer model as the digital model. The digital model will be decomposed or it will be sliced into finite number of layers. Then the information about the layers will be processed and the path will be generated. This path is nothing but the relative motion between the tool in the generative manufacturing process and the work part. We will be seeing one of the example of the additive manufacturing in the later slides. The generated path information will be given to the additive manufacturing equipment and the layers are generated, and by stacking the layers above each other we are developing the object. So, schematically we can see the 3D object is sliced into number of the 2D layers. The information about the layers will be utilized to generate the path. The information about the path will be given to the generative manufacturing equipment. There are many variants of additive manufacturing operation. Some of the operations you can see on your screen. These are the stereolithography with photopolymerization, selective laser sintering, FDM, that is fused deposition modeling, selective powder binding. So, this is nowadays we call the 3D printing, and the ballistic particle manufacturing. The stereolithography is the very first additive manufacturing process. However, the FDM is often being used. It is quite popular among the rapid prototyping applications of this generative manufacturing process. Well, for our study we can have a look at the fused deposition modeling process. So, on your screen you can see the typical arrangement of the FDM. The FDM process is carried out by depositing the molten thermoplastic material layer by layer. So, to deposit the molten thermoplastic material layer by layer, an arrangement can be seen on your screen. In this equipment there is a platform. This platform is arranged in a chamber. It has a roll, and this roll is having winding of filament, that is the raw material filament. Then the main part of this process is the extrusion head. The filament is fed inside the extrusion head. The extrusion head is heating the filament, and in its liquid state that filament will be extruded through the nozzle, and that extruded part would be put on the platform. The required deposition can be achieved by having the relative motion of the extrusion head with respect to the platform. So, this extrusion head can be moved along x and y direction. However, the platform is moving along the z direction. So, as we move the extrusion head, we can deposit the required material on the platform. So, after generation of one layer on the platform will be lowered. It will be moved into the downward direction. So, after the generation of a layer, the next layer will be deposited on the previously deposited layer, and in this way we can generate the 3D models using the fused deposition modeling. In this process, the solid filament which is used is a thermoplastic material. In general, the thickness of this filament is about 1.25 mm. The heating would be carried out in between the 80 to 85 degrees Celsius inside the extrusion head. The extrusion head is also having a volumetric pump which is precisely pouring the molten thermoplastic material through the nozzles. The deposition operation we are carrying out at the temperature just above the melting point temperature. The resolidification time is very small, that is 0.1 second. So, on your screen some of the models which are generated by using the fused deposition modeling process can be seen. So, here you can notice that very complex shapes can easily be manufactured using FDM. Here you can notice the thin parts also can easily be manufactured. In addition to that, this is an industry part. This is basically a jigs and fixture part which is manufactured by using the FDM process. So, some important parametric data can be seen on your screen. In general, the travelling speed of FDM is about 380 mm per second. We can have the layer thickness in between 0.025 to 1.25 mm. The FDM process gives us repeatability and positional accuracy about plus or minus 0.025 mm. The most common printing material which is used in FDM is ABS, that is acrylonitrile butadiene styrene. But my friends, we can also utilize or we can use the stainless steel, aluminum, copper or nickel superalloys to generate the 3D models using the FDM methodology. So, let us summarize this lecture. At the start of the lecture, we have seen various fabrication techniques, and then at preliminary level we have gone through the casting, forming, joining, machining and generative manufacturing processes. My friends, the detailed analysis of these processes is out of the scope. You can refer the other courses or you can refer the standard textbooks available to study in detail about these processes. In the next week, we will be studying the sensor technology, various sensors which are required in automation systems, and we will also see their principle of operation, the constructional details and its applications. So, with this I conclude this lecture. Thank you very much.